Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to my AP Physics exam preparation video series. Over the next several weeks, I will be releasing sample free response questions from each of the 4 AP Physics exams to help students familiarize themselves with what kinds of questions will be asked and how the AP Physics exam will ask them to demonstrate their knowledge. As a tutor working with students all over the country, I know that not every student has the opportunity to work with released exam materials prior to exam day, and this video series is intended primarily to help those students. AP Central lists the following types and number of free response questions on the AP Physics 2 exam. There will be one on experimental design, one that is a quantitative translation, one that is a paragraph length response or paragraph argument, and one that is a short answer. And the question in this video is type number 1, experimental design. We'll take a look at AP Physics 2 2019 free response question 3 on thermal conductivity. A group of students used the apparatus shown below to determine the thermal conductivity of a certain type of plastic. A hot plate is used to keep water in a container boiling at a temperature of 100 degrees Celsius. They place a slab of the plastic with area of 0.025 square meters and a thickness 0.010 meters above the container so that the bottom surface of the slab is at a temperature of 100 degrees Celsius. They put a large block of ice with temperature 0 degrees Celsius on top of the plastic slab. Some of the ice melts, and the students measure the amount of water collected during a time delta t. The students correctly calculate the amount of energy Q delivered to the ice and thus determine Q divided by delta t. They repeat this experiment several times, each time adding an identical slab to increase the total thickness L of the plastic. Their results are shown in the table on the next slide. So you can see here the data for the energy flow rate, Q divided by delta T in joules per second, and the total thickness of the plastic L measured in meters. The students want to create a graph to yield a straight line whose slope could be used to calculate the thermal conductivity of the plastic. Part 1, label the axes below to indicate a pair of quantities that could be graphed to yield a straight line. Include units for the quantities. So, let's take a moment here and note that we do have an equation for the rate of heat flow relative to, or as a, relationship with the conductivity of a material, and that's Q divided by delta T equals Ka, Q divided by the time interval equals the conductivity times the area of the material times the difference in temperature divided by the thickness of the material. So this gives us a nice guide that our horizontal axis should be 1 divided by the plastic thickness, and our vertical axis should be the energy flow rate. And and actually I'm looking here and realizing that the first point actually comes with the graph. So let's move ahead to talk about the graph and the data that we'll need, and then we'll talk about scoring. So on the grid, create a linear graph using the values for the quantities indicated in part A1. Be sure to do the following. Add to the data table the values of any quantities to be plotted that are not already given. Scale the axes, plot the data from the table, and draw a line that best represents the data. So note that I used a plotting software to do this. I did not plot this by hand. So we will need to add 1 divided by the thickness, which is 1 divided by L, measured in per meters, to the data table. You can see that we've done that calculation here. So here is the plot of our energy flow rate versus the inverse of the thickness. I made this graph in or this plot and did my analysis with a program called Graphical Analysis. It is a free tool available from Vernier. So I can go ahead and talk at this point about some of the points that were earned. The first point from these first couple of sections is for labeling the axes with 2 quantities. That would produce a linear graph, including units. And another point we could talk about at this point before we talk about the trend line would be for scaling the axes linearly. So the data extends over at least half of each axis. And a third point we could talk about at this point would be for accurately plotting the data. And now here is our best fit line. And our fourth point here is for a best fit line or curve, well, curve or line that fits the trend in the data. And you can see here that this plotting tool gave me a slope and a y-intercept and the R value that tells me how well a linear fit fits the data. And this actually looks pretty good. So I will be able to keep using this given slope in the subsequent parts, but I will also talk with you about what came out of the sample graph shown in the scoring guidelines. Part 3, use the graph to calculate the thermal conductivity of the plate. So if you recall, earlier I did show you an equation for this relationship, which is that rate of energy flow equals Ka delta T times the inverse of L. I wrote it as just divided by L. So this shows us that our conductivity is going to be related to the slope of the graph. I like the way that E looks. Hang on. Let's fix that. So I used, this plotting software and it gave me a slope. So I'm just going to use that value. It was 0.9736, but in the scoring guidelines, which I'm going to abbreviate SG, they show a calculation where the slope works out to be 1 joule times meters per second. And again, that came from the sample graph that was in the scoring guidelines. So our next step here is again going to say that our slope must be equal to K, the conductivity, times the area divided by the change in temperature. So K must be equal to our slope divided by A times delta T. Oops, that should be the 0.9736 times 0.025 times 100. And I actually would like to note for you, just thinking about the slope really quickly, you can use your graphing calculator to plot the data and get a linear regression. That didn't show up and wasn't addressed in the scoring guidelines for this question, but I've definitely seen it in other experimental design questions where, they will say, if you do a linear regression, this is the value that you get for the slope or for the y-intercept. So it is completely okay for you to do that. And you would just need to make note of the fact that that was your method that you used. So here we'll get a thermal conductivity of 0.389, and that's going to be actually 0.3894. I will leave it to you to decide how many significant figures or decimal places to keep. And that's joules per second per meter per degree Celsius. And in the scoring guidelines, they give a value of K that's equal to 0.40 using that slope that worked out to be 1. So here's our scoring. We're going to have, I manage to do that every time. I just lose track visually of my cursor. I'm just going to leave the squiggles there. 1 point for a correct method. For calculating the slope. This is key. Using points on the best fit line. You cannot use actual data points. Let me just erase that. Fix this, make it look a little bit better. You can't use points on the data points. Sorry, you can't use points on the. You can't use data points unless they're on the best fit line. Sometimes I cannot speak and write at the same time. Okay? This is my note, not data points. Only use data points to get your slope if they're on the best fit line. And then our second point here is going to be for determining the thermal conductivity K with or without units using the slope that you found. Part B, indicate one potential problem with the setup that could lead to an experimental value for the thermal conductivity that is different from the actual value. Use physics principles to explain the effect this problem could have on the experimental value. So there are actually two problems, and we'll talk about both, then we'll talk about scoring. One problem is that the given setup allows energy to be transferred to the ice from the air around it. This means the values of Q divided by delta T contain energy that did not go through the plastic slab, resulting in a value of K that's too large. The other problem is that the given setup allows energy to be lost out the sides of the plastic slab. This means the values of Q divided by delta T do not contain all the energy that went through the plastic slab, resulting in a value of K that's too small. Students picked one or the other to talk about, and you don't have to address both because it wouldn't make any sense for you to say, my K is both too large and too small. Pick one, talk about it. But I wanted to point out that there was more than one right answer. So, here is where our points come in. We're going to get a point for any indication, any valid indication. Ooh, that matters. That word is important. Valid. Of additional thermal interaction with the environment. And then our second point is going to be for a reasonable explanation of how additional energy added or lost could change the experimental value of conductivity. Part C, the rectangle below represents a side view of the plastic slab. Draw a single arrow on the diagram representing the direction of the net flow of energy through the plastic. Well, energy flows from hot to cold. So bottom to top. And our point here is going to be 4. Drawing an arrow toward the top of the page. Part D, describe what occurs in the plastic at the microscopic level that explains the energy flow you indicated in Part C. Energy absorbed at the lower surface makes particles vibrate faster. They jostle particles above them, and so forth until the energy reaches the other side. There was a lot in the scoring for this one, so I have it typed. +1 for indicating that particles at the bottom, or a location consistent with Part C, have higher temperature or kinetic energy, so they vibrate faster. And then the second point is for indicating that particles collide with neighboring particles, transferring energy from faster to slower particles in the process. Part E, an extra plastic slab sits on a wood surface with both the plastic slab and the wood surface at room temperature. A student touches each and finds that the plastic slab feels cooler than the wood surface. Explain what causes this observation. The The slab and the wood have different thermal conductivities, which means that they absorb energy from the student's hand at different rates. The one that has the greater rate of absorption feels cooler to the touch because it takes energy from the student's hand faster. So our point here was for indicating that the slab and wood have different thermal conductivities, or that energy is transferred into the plastic and wood at different rates, with no incorrect statements. So I hope you have found this demonstration of an AP Physics 2 experimental design question helpful. If you have a video solution request for my YouTube channel, you can send it to physicsproblemrequests@gmail.com, but I won't be putting up any other videos until my AP series is concluded. If you need some email assistance, you can send your problem and the work you've done on it so far to freephysicshelpline@gmail.com, and there's a limit of 10 questions per academic year. If you'd like to learn more about my online physics tutoring services, you can email me at brandyheflinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. So just a few notes. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All of the materials presented are available on AP Central at the link shown here for the AP Physics 2 exam, and those materials include the release free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different levels and quality of the responses prepared by the students who took these released exams live, and to see what the scores for that year were looking for and how they decided to award points. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.